challenges that we face in the area of energy, but seen from a systems theory or from a more mathematical point of view. Before I start, I would just like to say that it's a rather generic presentation. So for people like Janusz here, power systems expert, it is going to be slightly boring. And I promised almost no equations, okay? So with this in mind, let's start. We're going to see three different things. As I said previously, the current research challenges. We're going to see a few things about what types of energy storage technologies we have. And then we're going to see a few things of our work at Newcastle University. So this is what people call a fit and forget power network, a traditional power network. There are two main characteristics of this power network. The first one is that usually the energy is being produced far away from the end user. And secondly, the flow of energy is only in this direction, from the power plant to the end user. I think that several speakers have mentioned various problems with these power networks. I think it's pretty much obvious that you'll have losses. It's a very old network and so on. So on this, let's say, not best power network, instead of trying to do something to help it, you do something completely opposite. You smash it with a sledgehammer. You try to electrify heat and transport. Okay, just to give you an indication, if you are not an expert on power systems, this is real results. Okay, so these are the actual power that is being consumed in a typical UK house. If I remember well, these are from CLNR. And this is the energy and the power that you need if you buy one electric vehicle. I'm sure that the impact is huge, and this is obvious. Now, some people, especially power network operators, experts, they will say that this is not exactly true, because not everyone will charge his or her own vehicle at the same time, at the same rate, and so on. Absolutely right. We must see the average picture. However, as we buy more and more EVs, this will come closer and closer to reality. Another interesting figure to understand this sledgehammer hit is this one. We can see here how much energy we use for electricity, how much we use for transport, and how much we use for heat. Now, obviously, you cannot just simply add this trace and this trace and this trace to see the impact, but I'm quite sure that everyone can immediately say that if you take part of these traces and you place them here, the impact to the power network will be huge. Okay, so let's build more nuclear power plants. Yes, the problem is not producing this energy. The problem is transmitting this energy. So it is the infrastructure, it is the transformers, the cables, the substations. This is our main problem. I think that someone else mentioned this previously. Okay, let's reinforce our power network. Let's put more cables, more transformers, more substations. Yes, but this is not very cheap. It is very expensive. And our power network is already huge. If you place our power network on a straight line from this point, you can go to the moon and come back. So just by adding more cables, it's not going to solve anything. Okay, then what? Let's make our power network more eco-friendly. How can you do that? Already has been said, add renewable energy sources. Great idea, right? Well, it is a great idea. However, there are three problems when you add renewable energy sources. First of all, you make your power network, let's say, robust. You go away from the previous model of having 5, 10 big power plants and sending energy to the end user, but now you have tens of thousands of small power plants, PV panels on your roofs, and hence the previous model changes completely. And for me, this is the biggest problem now. There are two issues here. The first issue is, can we predict how much power we're going to produce? Okay, people talk about short-term prediction, long-term prediction, and so on. Let's assume that your machine learning algorithm, your GAs, and so on, they're just so great, and they can tell you that after 2 weeks, the expected power from the PVs is, let's say, 8 kilowatt hours. How about if you need 10? as my main background is on control theory, it is fundamental for me that I cannot control my renewable energy sources. So if I would get 8 and I need 10, somehow I need to find 2 extra kilowatt hours. So simple. And now on all of these problems, our end user, it's not end user anymore. The end user now will produce also power, and hence you have the prosumer, will store energy, will sell energy to the power grid, and also, hopefully in the near future, we may have peer-to-peer exchange. So we talk about a completely different model. So even if you see this from a legal point of view, from a business model point of view, you have something drastically different. We also talk about demand-side response. I think the previous speaker mentioned many things about this. So challenges here, you must see how can you aggregate 1, 2, 10,000 users in order to have a meaningful demand-side response. So all of these problems here on our old power network, we claim or hope, to be more precise, that they can be addressed or partly solved better by using energy storage. And you don't have to trust me or to believe me. The International Energy Agency also states the same thing. You don't have to go through all of these things now. Very, very briefly, they say that we have a very old power network. We need to electrify heat and transport. This will put a huge impact on our power network, and for that reason, we need energy storage. So we go away from the previous traditional fit and forget power network to something like this, to a smart grid. You still have the old power plants, and I know that the topic of this workshop is about 100% renewables, but if you want me to be honest, I don't think that for the foreseeable future you can achieve 100% renewables. So you will still have this old power plant, but now you have several or thousands renewable energy sources. You combine this with hybrid storage. I'm going to explain this later. This is really important. You have smart sensors everywhere, and you can isolate your parts of your network if something goes wrong. So the challenges and the flexibilities here are huge. Okay, so for example, you can go to a big industrial plant and combine it with a set of renewable energy sources and energy storage, and make it behave like a virtual power plant. So for the rest of the network, this can be seen as a virtual power plant. This is a very nice figure. I really like it. I show it to my students, very nice, but not very practical, I have to be honest. I like to see what is a smart grid from a purely systems theory point of view. And this is what I think is a smart grid. And through that, we will be able to see the research challenges. You start by having the traditional power network. So all the problems and the design questions that we know from the previous years are still applying here. But now on this network, you add something else. You add energy storage, you add demand-side response, and renewable energy sources. So now you add more questions. Where are you going to place your renewable energy sources? What types of storage are you going to use? How can you change the business model to achieve meaningful demand-side response? And now on this very complicated power network, you add another layer. You add an IT network. You have all of these smart sensors, and they exchange information. So research questions there, fast and secure communication, cyber security, and so on. And on top of this very complicated thing, you add a control network. And this is my background, so I left it for the end, okay? So you need to control now all of these assets. How are you going to control it? So what is the energy management strategy? How are you going to control which assets will be on, off, and so on? Not only that, what type of controller are you going to use? Are you going to have one big central controller here, or are you going to have several local controllers? What is a local controller? Will one controller control one asset or several assets? So we have theories here like multi-agent systems, network theory, graph theory, that they can be really helpful. So if I would like to pause a little bit and show you in one slide the main research challenges stolen by Phil Taylor's presentation, to be honest, I would use this slide. So we need to answer these 3 Ds. Obviously, we need to have a more environmentally friendly power network. In order to do that, we need to use renewable energy sources. So we must almost redesign our power network and go to a completely different topology. How can we exchange information? How can we control assets? We need to digitize our network, our energy network. And we have to do all of these three different things when we have a highly uncertain system. It is uncertain because you don't know how much power you're going to produce, you don't know how much energy you will demand, and also you may have other discrete events. So it is a hybrid system with a true meaning. I'm pretty much sure that everyone can understand it is a highly complicated system. It is a very coupled system when one small change here can create something hugely disruptive somewhere else. And as I think the first speaker mentioned, or the second, we need to be flexible. Okay, so flexibility, we need to be able to control everything, from the power that we generate, to the power that we use, to the power that we store. Okay, so these are the 3 main challenges. And as I previously said, we hope that we may be able to do that by using energy storage. But as we all know in life, once you have one answer, you have 10 more questions, right? So what types of services are you going to use? How can you maximize your income? This triplet here, I think it's really important. Are you going to have one small battery in your house? So let's say, I don't know, Tesla's Powerwall, or are you going to have a medium-sized thermal storage unit in a small village? So all these are really important questions. But I think that this is also very important. Every time when we use an energy storage asset, we reduce its lifetime, its capacity. So it could be a possible scenario where you can have stored energy in your battery, but the price from the DNO may be cheaper. It may be better to take energy from the network operator. So we have to be very clear about all of these things. There are other issues like social behavior, like legal issues and so on, like who owns, who operates these assets. Are you going to put them behind the meter, after the meter, and so on? How can you aggregate so many users so that you can have meaningful impact on the power network? As I said, control and Internet of Things and cloud, I'm going to talk about this too at the end. So all of these are my current research challenges. And of course, we need mathematicians to address these challenges. Very, very briefly now, regarding storage technologies, I have grouped them here into 5 different areas: mechanical, thermal, electrical, electrochemical, meaning batteries effectively, and hydrogen, even though you can group them in different ways. All of these now different types of energy storage, they have different properties, like energy density, power density. So for example, a supercapacitor has high power density, but not so high energy density. Efficiency, response time, and so on. I think one column here that it is hugely important, it is this one. How mature is a specific technology? So again, from the same report, we can see that some types of energy storage, like pumped hydropower, they're very well known. We use them all the time. But some other, like for example, superconducting material, we are not so familiar in the area of energy storage. So we have to be very, very carefully, we have to choose carefully which energy energy storage technology we're going to use. And now we go to even something more complicated. We go to hybrid energy storage systems. Why hybrid? I previously said that each technology has its own properties. So how about if I combine 2, 3, 4 different types of energy storage, and by doing that, you have the benefits of all types, okay? So this is the first energy system that I did some work on 6, 7 years ago, I think. I had to design, model, simulate, build, and test and optimize eventually this isolated microgrid. We can see that to have renewable energy sources, we have this as a backup, obviously. We have the battery here for what people call short-term storage. So you charge it during the day, you use it during the night. And then once this is completely full, you can make some hydrogen here, store it, and then use it later. This is for long-term storage. So for example, you can create some hydrogen, excuse me, during the summer, use it during the winter. I like this graph. When I read this paper, I was really impressed, to be honest. Look at this path here. You can actually take energy that you produce from nuclear power plants, for example, make it methane or hydrogen, pump it into the gas grid, send it wherever you want, and actually then you can even produce some electricity once again. I know, there are so many questions here, like efficiency and so on. I agree. Actually, this route will be highly inefficient. However, imagine the benefits. This grid here, this network here has no losses, or almost no losses, hopefully. So it is really important that we combine different types of energy storage. I'm sure that you have heard about combining supercapacitors and batteries in EVs. Very important to see the services that we are going to offer. So how can you choose better our services? Again, stolen from this report, you can do all of these things. I'm just going to focus on 3 main topics. I think the first one is pretty much obvious. You store some energy when you have surplus, and then you can use this after days, weeks, months, and so on. Frequency regulation. For the non-experts, very, very briefly, if you have an area of your network where you produce more energy than what you consume, it is possible for the frequency to increase, and of course vice versa. So you need energy storage to avoid this problem. Demand shifting or peak reduction or peak shaving and so on. If you can predict that after a few hours you are going to have high demand, it is possible to use this stored energy in order to make sure that the DNO will not see this high peak. So a few things now about Newcastle. I can see several people here, and of course Chris here from CESI. CESI is the National Center for Energy Systems Integration. 4 main universities, strong links with industry. Our main goal there, our main aim there is how to integrate different energy carriers. How can I combine gas, heat, and electricity, for example? What are the benefits? What are the challenges? People talk about time constants, okay? Imagine that these networks, they have completely different time constants. What will happen when you combine them? How can you build new business models? And so on. How can you study the social behavior of people, okay? So effectively, we try to do all of these things. One thing that I would like to pause here for a few seconds is this one. I think living labs is something that will be extremely important in the near future. We're going to see very, very briefly how people can interact with all these technologies. Okay, so also in Newcastle University, we are very proud for our facilities. This is our energy test bed. Effectively, you can test various types of energy storage, like various types of batteries, supercapacitors, and so on. You can connect it to the main grid, so you can send energy to the main grid, and you can take energy from the grid. I like this one. You can emulate any storage technology you want. So you may have your fancy, fuzzy logic, neural networks, machine learning algorithms for modeling, for control, for exchange of information. We can test all of this in real life. Okay, I'm going to skip this. I just wanted to say that you have been involved in some rather large projects where we installed large batteries. So how can we design, how can we choose these energy storage assets? And this is what we do in Newcastle. I'm more or less sure that everyone in this room who is a power systems expert, well, he or she will do the same thing. From our perspective, the first thing is we need to see what types of services you are going to use, you are going to offer to the end user. So in this work, David, my colleague, took this approach, okay? Let's say that you commit to one specific service, peak saving, for example. As we all know, we are not offering this service all the time. So the question here is it possible, is it good for us to try and say, can you choose also at the same time other services? And of course, in order to do that, we need to run several simulations. Well, most of you here are mathematicians, and you can imagine how many scenarios you're going to try and predict how you're going to maximize your revenue and so on. Several people have said it already, but once again, for the non-experts, one key element here is statistics, okay? So most of you are experts in this area. We have to do a lot of, we need a lot of help in order to see how can control our assets. We can see here some results where we try to predict a state of charge, state of health, and so on. How can you size and choose the energy storage technology? Very, very simple. This is an optimization problem, as you have already seen. You have to choose your objective functions, your constraints. In this paper, we use linear programming, but of course you can use various other methods. Our task here was, we have this wind farm, and we want to maximize the benefits from building this wind farm by using different types of energy storage. And we also want to offer various services to the network operator. So without getting into any great details, what I would like you to see from this figure here is this. Depending on what services you are going to choose, you have to choose the right technology. So for example, here we can see that we can maximize our revenue, while here we have a loss. So choosing the right combination of services and technologies is crucial. End-to-end modeling, this is the bit where I am slightly more involved. Well, this is, if I remember well, a paper between Newcastle, I'm not quite sure, Birmingham, and definitely Imperial. So we have here at a molecular level a very detailed model of a battery. And then we combine now this very detailed model to a power converter. Just try to imagine now the things that you need to investigate here. My main background was on power converters and how to study their nonlinear or chaotic behavior. Most of you will probably know that these switch systems, you may have non-smooth bifurcations. When these things happen, you can go from a normal period to one operation to chaos immediately. When you have a chaotic system, it is uncontrollable, unobservable. So it's really, really important for us to know when these things happen and how you can avoid them. And now you take this expanded or combined model better and you put it in a real network model. So you go from the molecular level to the grand power network level. And you can see how all of these things interact. And hopefully I have time, and I'm going to show you some interesting results, which I found very, very surprising. Once again, for the non-experts, floating state of charge is the state of charge when your battery is doing nothing. So we have here two traces here, okay? The blue trace and the green dust trace. The blue trace is when the floating state of charge is 100%. So you start these tests by having a fully charged battery. Look at the loss of life. The loss of life is far bigger when you have a fully charged battery. So someone may say, okay, Damian, how about if I don't have a fully charged battery? You're absolutely right. But then, if at this instant the operator asks from you more services, you cannot offer them. So we have to be very, very careful of how we're going to design and control our system. Once again, optimization problems, stochastic systems, and so on. More results here, I can skip them. Yes, one thing that is very important and was contradicting the previous statement was that the efficiency was dropping when the floating state of charge was reduced. This is something that I'm more involved. I apologize for this one here. We try to use multi-agent systems, graph theory, network theory, propositional logic, and so on, to model and control microgrids or energy systems and their energy management methods. So this is the key point here. We do not only try to model the network or the grid, but we also try to control the control actions. And this is how you can represent this microgrid as a directed graph. And these are some nice, elegant, for me at least, statements of how you can control these assets. By doing that, you were able to understand how complicated and uncertain systems behave. By understanding how these systems behave, we are able to offer more energy management methods. So in this specific paper, we took our previous system, we combined with 2 other similar systems, and we tested various energy management methods. And these 30 different energy management methods were only able to be derived because we understood how the system behaves. So look at this. This is the amount of using the diesel generator or importing energy from the main grid. In the basic standard, if you want, energy management method, we needed all in 1 year, sorry, I forgot to mention that. In 1 year, we needed 1,500 hours of operation. In some other methods, complete autonomy. So this was extremely useful for us. I'm going to skip that because you have already seen that. Let's talk about cloud now. Well, this is a project that we do with Siemens. You may have heard about MindSphere. Very, very briefly, because my time is running out. You have your batteries, but also any other asset. To be honest, you have your sensors. You send information on the cloud. There you do your fancy machine learning methods, neural networks, and so on. You take some decisions, and then you send the control signals down to the assets. And very, very briefly, only 10 seconds, about this project that has just started. Very, very briefly, it is in a collaboration with Imperial, DNOs and DSOs, sorry. And very, very briefly, we try to see now our EVs not as a big load, as you have previously seen, but as a mobile or a moving battery. And once again, try to imagine the complexity and the uncertainty here. How are you going to drive your vehicle? How long, how fast, and so on. So all these things need to be answered by great mathematicians in this room. So hopefully I'm on time.
Excellent.
Thank you.
Thank you very much. We have 3 minutes for questions. So any questions, please?
No, so yeah, Patrick. That's very interesting, and but so realistic. Yes, so you need to have realistic modeling on everything, and I saw some loop, like for example, the water that you can recycle in your system. It's not so obvious. The purity of the water is a big issue.
Right.
The same for the storage of hydrogen is a big issue. So there is a lot of technical issues that are not so simple, and
I agree completely.
Demonstration on that, and we are aware of that. And the same for the vehicle to grid. So perhaps the design of the battery for a vehicle is not the same that the one that
you're absolutely right.
To support the grid. So some people say that we can do something, but when you
try to do it,
you need a specific technology for the grid support that is not the same.
Yes, exactly.
So at the end, all these synergetic effects that are very good, but sometimes they are a bit theoretical.
I think it's too early to have a definite answer on all of these things. But I think we are going there. Maybe not yet there, but we are going there.
But of course, we have to dream to do something. But
yes,
dream.
Okay, thank you. Yes, please, Andy.
So batteries have various uses, right? As you showed, you can forestall investment in distribution assets. You can control frequency. You can arbitrage prices.
Yeah.
The different agents in the market, like a distribution company, or at least in my part of the world, control monopolies, and they're not allowed to actually trade energy.
Okay.
So other
That's
agents
interesting.
can trade energy, but not only so. But that's not enough to pay for the battery. So do you have any idea of a mechanism by which these things could be
Well,
combined? There are different agents having not enough benefit from the battery on their own to pay for it.
this is probably the area where I know almost nothing. So I'm not an expert in this area, so how to combine different agents and so on, I really cannot answer that story. But it is a very valid point. We have done some work, not regarding legal issues and so on, but in general. So we try to see solutions that are very good for the UK power network, if they can be applied to Malaysia or Singapore. It's a completely different answer there.
Thank you. Last question. Over there, please, Leon.
So, just going back to one of your early slides where you showed the single sort of smart grid, should we be changing our thinking from thinking about a single integrated system to thinking about regions or areas which are kind of self-sufficient and with the long-distance transmission kind of providing supplementary services, if you like, as an exceptional thing rather than as the base?
I think that this can be something for the future. Oops, sorry. Yes, so it is possible, but I think it is the same answer as the gentleman over here, that I think it's still too early to know what is the right path to go forward. But integrating various technologies, integrating various energy carriers, and talking about small parts of the network can be the way forward.
Maybe Kathy wanted
So
to ask
just
from
to
National
comment
Grid.
on that from the UK perspective, I think where you've got a national problem like managing system frequency, it makes sense to do that on a national basis, so energy balancing, and only deal with managing local regions where there's constraints, because that gives the best cost to consumers. But where you've got local problems, you can solve those with local markets. So national problems, national solutions, local problems, local solutions.
Thank you very much. Thank you very
Thank
much, Damian.